Hi everyone, as Armando said, I'm Isil Dillig from UT Austin. I'm one of the PIs on this project, and today I'm going to tell you about some recent work that we did on improving program synthesis by really combining the power of deductive reasoning techniques and machine learning, in particular reinforcement learning. And in contrast to some of the synthesis talks that you heard yesterday, this is going to be a more deep dive kind of talk. So I'm going to talk about some of our recent work in a bit more technical detail. And this was joint work with Osbert Bastani, who's one of the PIs on this project, my former PhD student, Yu Fang, and our current PhD students, Yanju Chen and Chenlong Wang. Okay. So first of all, from my perspective, program synthesis is fundamentally a very difficult search problem that's akin to finding a needle in the haystack. And here, in this case, this needle is a program that needs to conform to certain syntactic and semantic requirements. And in particular, the syntactic requirements are defined by your context-free grammar, and the semantic requirements are in the form of your specification. And as we all know, this search problem is so difficult that there's no way you can brute force it. And in the synthesis community, we have two powerful weapons that we've been using, namely deductive reasoning and machine learning. So before I continue, first I want to say a few words about how deduction and machine learning have traditionally been used in the context of program synthesis. So on the machine learning side, we typically use statistical models for guiding or prioritizing the search. So in particular, there's some offline phase where the goal is to train a statistical model that can predict the likelihood of a program conditioned upon some specification. And then once you have this model that you've trained offline, then at test time or at synthesis time, you can use this model to prioritize the enumeration of programs that are deemed more likely by the model. So you want to enumerate more likely programs before less likely ones. Now, on the other hand, if you look at the way deductive reasoning is used, it's used for an entirely different purpose, namely for pruning the search space rather than prioritizing or guiding the search. So for example, if you're doing top-down enumerative search, you can use some form of deductive reasoning to check if the partial program is feasible or not. So to elaborate what I mean by that, let's consider this partial program that I'm showing on the slide. So this is represented as an abstract syntax tree. And here X corresponds to the program's input. Filter is just a simple function that does a filter operational lists. You have this take component, which gives the first n elements in the list. And let's say head gives you the first element in the list. And the question marks are the unknown component. So that's why this is a partial program. Now, to see how deduction is useful, let's say we're given this specification that you see at the bottom. So some input list, that's our input. And let's say we want our output to be 312. Now, even though we obviously can't execute this partial program because some pieces of it are unknown, we can actually use a form of program analysis or form of deductive reasoning to say this partial program can never satisfy this specification. And this is the case because all of the components, filter, take, head, and so on, preserve the elements in the list, but this specification says that the output is a different element than the elements in our input list. So therefore, using this kind of reasoning, we can use deduction to prune out large, infeasible parts of the search space. Now, it turns out that paper after paper in the synthesis literature has shown that both machine learning and deduction are extremely useful for making synthesis tractable. But really, if you think about it, the way they've been used, they kind of each live in their own worlds. Machine learning does its own thing. It's used for guiding the search. Deduction does its own thing for pruning. But really, there's no kind of meaningful interaction between these two modes of reasoning. So this is where what we were trying to address with this work. So how do we obtain this tighter coupling between statistical and deductive reasoning? And in particular, the question we ask ourselves is, can we use the feedback that's provided by the deduction engine to improve our statistical model during synthesis time? And as you can tell from the title of this talk, we do this using reinforcement learning. And in particular, our goal here is to train our agent, in this case, the synthesizer, so that it can learn from the consequences of its own actions as it explores the search space over programs. And in reinforcement learning, the agent receives some sort of feedback from the environment. And in our case, the role of the environment is played by our deductive reasoning engine. Okay, so now let me give a kind of an overview of how this approach is going to work. So first of all, similar to a lot of prior techniques on program synthesis, our framework is based on top-down enumerative search that's guided by a statistical model that has been trained offline. So in other words, in the rest of the talk, I'm going to assume we have this initial model that's been trained offline. And this model takes as input our specification and the current partial program, and it produces a probability distribution over grammar production. So in other words, it will tell us which grammar productions are useful for expanding the current partial program. So at every step in this process, we have our partial program, and we're going to consult our statistical model to figure out how to expand this partial program. So if you look at this partial program on the right-hand side, you know, the initial model might say, well, you should probably, it looks like we're promising to expand N2 with this component filter. Now, also similar to prior work, once we have a partial program, we're going to invoke some sort of deductive reasoning engine to check whether this partial program is feasible or not. And in this case, it is. So we go back to expanding. So let's say it tells us, let's expand N4 with X. And again, we invoke our deduction engine. But now at this point, if we're still dealing with the same specification I showed you earlier, now the deduction engine can prove this program is infeasible for the reason I explained earlier. Now, here is where the difference in our approach comes into play, because rather than just, ruling out this one partial program, what we're going to do is we're going to use the feedback that's provided by the deduction engine, and I'm going to elaborate on what kind of feedback it provides in more detail later. But we're going to update this feedback to update our statistical model so that the decision-making capabilities of the synthesizer improves over time. And the way we update the model is based on reinforcement learning. Now, as you all know, whenever you talk about reinforcement learning, it's useful to have some sort of Markov decision process formulation. So to explain how our approach is going to work, so first let's see how we can think of program synthesis in terms of a Markov decision process. So to remind everyone, an MDP is a state transition system where you have some states, you have actions, you have transitions. And importantly, you have the notion of a reward. So basically, you get positive reward for doing something good or useful, and you get negative reward for doing something bad. So how does this relate to program synthesis? So in our context, we're going to think of actions as productions in our context-free grammar, and the states will be partial programs. So in other words, taking a transition means that expanding a partial program using one of the productions in your grammar. So that the transitions will take for this partial program and this CF2 production, you get this new expanded partial program. Now, when you talk about MDPs, we also have a notion of an initial state distribution and the notion of a terminal state. And in our case, this is very simple. The initial state will just be the start symbol of the grammar, and the terminal states will be points where the search reaches a dead end. So in other words, either successful synthesis attempts or points where you have a partial or complete program that the deduction engine can prove to be infeasible. Okay. And then in our context, you can define reward in more sophisticated ways, but let's say in this work, we're going to define reward very simply. So we're going to say you get positive reward +1 if you find a program that satisfies the specification. You're going to get negative reward if you have a partial program that's infeasible. And everywhere else, you don't get any signal. So we're just going to say the reward is 0 everywhere else. Okay, so now once we have this MDP formulation of program synthesis, you can think of our statistical model that's used to guide search as a policy of this MDP. So in other words, the model or the policy is going to tell us for a given partial program, it's going to give us a probability distribution over grammar productions to use. And as standard and reinforcement learning, our goal here is to find a policy, pi, that's going to maximize the expected reward, j of pi. So in other words, we want to start with an initial policy, which is the policy that's trained offline, and then we want to gradually improve this model by updating our policy. So let's see how this works in more detail. So first of all, our technique builds on a standard reinforcement learning technique called policy gradients. So for those of you who may not be familiar, let me first just quickly give the key ideas behind policy gradients, then I'll explain how we're going to adapt it to our setting. So first of all, policy gradient, this technique assumes that your policy belongs to a differentiable parametric policy family, and the parameters here are denoted as theta. And in our case, we're going to be using deep reinforcement learning. So this policy family is going to be a neural network. And of course, our goal is to learn or improve the weights of the neural network in a way that will improve the expected long-term reward. And the key idea underlying policy gradients is to improve the policy by using gradient ascent. So basically, you start with some initial policy and you improve the policy by taking a step in the direction of the gradient of j of pi. So since j is the expected long-term reward, taking a direction in this gradient of j of pi allows you to improve your overall reward. Now, the key question that's addressed by the policy gradient theorem is how to compute the gradient. And basically, you do that by sampling rollouts from the policy. And in our context, a rollout is basically a partial program that's either satisfies the specification or that the deduction engine can prove to be infeasible. And the idea here is basically to estimate the gradient in the following way. So don't get scared of by all the math. So basically all this is saying is to estimate the gradient, you sample a whole bunch of rollouts. Then for each rollout, and in our case, remember a rollout is a partial program. So for each rollout, you compute this L value, which essentially you can think of it as the sum of different directions in the parameter space weighted by their future reward. And then you can obtain an estimate of the gradient by taking an average of all these L values for the rollouts. Of course, the bigger your N value, the better of an estimate you have. Okay. So now one kind of wrinkle in our case is that the deduction engines used in modern synthesizers don't just tell you this partial program is feasible or it's infeasible, but they can also provide richer kinds of feedback that we would like to leverage. So in particular, if you have a partial program that's infeasible, many synthesizers can do some sort of root cause analysis and they can tell you a whole bunch of other infeasible programs that are infeasible for the same reason as the partial program that we just explored. So for instance, we described an instantiation of this idea in our PLDI 18 paper, and there have been many other papers, both from my group and others, that can do this kind of reasoning and give you other kinds of infeasible programs when you have a problem. So before I continue, let me just quickly elaborate on what I mean by this. So again, let's go back to our running example where we have this partial program. Now, consider replacing this head component in our partial program with another component like max or min or last. Now, remember, we know that this partial program was infeasible because it preserves the elements in the input list, but we know that other functions like max, min, last, and so on also are element preserving. So therefore, if we replace this head component with either of these three, we can guarantee that the resulting partial program will still be infeasible. So similarly, with using the same kind of reasoning, if you take this take component and you replace it with something like a reverse or sort, again, for the same reason, because these are all element preserving, you will still get something that is infeasible. So basically, long story short, as you can tell from this example, given an infeasible partial program, you can do some sort of root cause analysis and you can infer many other infeasible programs. So for instance, in that PLDI 18 paper I was referring to, we do this by encoding the specification of the partial program as an SMT formula, and then we use ONSAT course to find these components that you can replace components in the partial program with. Okay, so now that we know what kind of feedback deduction engines can provide, so clearly, whatever the deduction engine gives us, we would like to use this kind of rich feedback when we update the policy. But here, one kind of issue is this standard policy gradient technique assumes that the rollouts that we sample are coming from the original policy. However, if we consider the partial programs that are returned by the deduction engine, these are not sampled by the current policy. These are coming from some reasoning that's done internally by the deduction engine. It has nothing to do with our current policy. So in order to make it possible to leverage this kind of rich feedback from the deduction engine, we use an off-policy variant of the policy gradients technique. And the way we do it is in the following way. So once we have a rollout, once we have an infeasible partial program, we use the deduction engine as before to obtain a bunch of infeasible programs. And then for each infeasible program, we're going to pretend that they're actually sampled using the current policy. But of course, they're not. And then to account for the fact that they're coming from a different distribution, we're going to use the standard importance sampling technique. So just to kind of refresh everyone's memory, importance sampling says that if you want to compute an expectation of some variable x that's sampled from a distribution G, you can compute it by sampling values from a different distribution F. But then to account for the fact that it's coming from a different distribution, you need to weigh the sampled values by G of X divided by F of X. So in other words, if you're a lot more likely to sample this value from distribution G as opposed to F, then that's going to get a big weight. But if you're a lot less likely to sample G compared to F, then you're going to get the small weight. Okay. So how does this work in more detail? So as I mentioned, we basically sample a rollout and then we invoke the deduction engine to compute all these infeasible programs, P1 through Pn, and typically the deduction engine will be able to give you a large number of these infeasible programs. Now what we're going to do is we're going to use these infeasible programs to estimate the gradient. And basically here, this equation here is basically just a simple adaptation of the standard policy gradient theorem. So as before, it's telling you, you basically take the weight, you take the average of these L values for all of these partial programs for all of these rollouts, but then you account for the fact that these programs are returned by the deduction engine as opposed to the current policy by using this importance sampling term. So for example, here, the numerator corresponds to the probability of sampling this partial program from the current distribution, and the denominator is the uniform distribution because we take all the programs that are returned by the deduction engine. Okay, so that's kind of the technical idea in a nutshell. Now let's talk about if this technique is actually useful in practice. So we implemented all these ideas in a synthesis tool called Concord, and we evaluated on 100 pretty challenging synthesis benchmarks used in prior work. And to give you a flavor, we looked at list manipulation benchmarks that are written in a functional DSL. And we took this DSL that's been used in prior papers, starting from DeepCoder. And we compared our approach against two different synthesizers. So one of our baselines is Deepcoder. And this is a very relevant baseline because it also does top-down enumerative search that's guided by a statistical model. And in fact, we use the same model that's used by Deepcoder inside our implementation. And in addition, we also compare against NEO, which is our tool from PLDI 18 that I referred to earlier. And NEO basically builds on top of Deepcoder. It again uses the same statistical model. And on top of that, it uses deduction. So basically, it does deduction to infer these infeasible partial programs, and it blocks those programs. But unlike our proposed approach, it will not update the initial statistical model. It just keeps using the same model all along during the synthesis process. So here on this slide, I'm showing, kind of giving a quick overview of the main results. So the x-axis here is the benchmarks, and the benchmarks are sorted according to how long these tools take to solve them. And the y-axis is the cumulative synthesis time. And basically the key results here is, and let me explain the different lines. So the brown line is Concord, which is our tool. The yellow line is Deepcoder, and the purple line is NEO. And here, as you can see, Concord can solve significantly more benchmarks than Deepcoder, and it can also solve more benchmarks compared to NEO. And when I say solve more benchmarks, that's within a given time limit. I believe the time limit in this case was 10 minutes. But on top of that, for all of the benchmarks that can be solved by all three tools, Concord's running time, average running time, is also significantly faster. So Concord has the average running time at 36 seconds, whereas NEO is 100 seconds and Deepcoder is over 200 seconds. Okay, so this kind of gives you a global picture of the results. Now you might wonder, well, I talked about kind of this adaptation of policy gradient. Do you actually need this off policy variant? Well, what happens if you just use more straightforward feedback that you get from the deduction engine? So to answer that question, we ablated our technique. And what we did is we basically just used the deduction engine to just get a feasible or infeasible signal so that we could just use a standard policy gradient to solve our problem. And here in this table, Concord is the full tool, whereas the second line, Concord standard PG, is the ablated version that's just using the standard policy gradient. And as you can see, Concord here can solve both more benchmarks using our adaptational policy gradient, and it's also faster. Okay. So I'll conclude there, but just the key takeaway here is that you can really marry the power of deductive reasoning and statistical reasoning. And in this work, we did this using reinforcement learning, and you can use this approach to improve your statistical model at synthesis time. So that's all I have. If you have any questions, I'm happy to answer them.
I've got a question. Isil, so great talk.
Thank you.
What do you anticipate your future work will be as far as evolving the different types of formal methods and machine learning techniques beyond what you're using right now with deduction and reinforcement learning?
So I view what I've talked about as kind of like a starting point. So I'm a big believer in that we need to be both using deductive reasoning and machine learning and making synthesis tractable, but this is just like one point in the space. So for instance, other things that I'm interested in is how can you use these kinds of like this synergy between machine learning and deduction to decompose the problem. How can you customize synthesizers to individual use cases? How can you better interact with users? So I think there are lots of problems that we can answer here.